Earlier in the video, I spoke at length about the importance of ensuring data consistency by associating a unique identifier of some sort with every record. The business case for ensuring the ability to uniquely do so should be obvious. Each customer doing business with our hypothetical company is unique, having over the course of time established, among other things, a characteristic product ordering history and customer service relationship. Therefore, when consulting the database, it is crucial that a staff member is able to identify without error the desired customer. This can be more difficult than it may seem because customers often share identical attributes, residing in the same city or state, and even sharing the same name, despite residing in geographically disparate locations. So attempting to search the database using one of these potentially shared attributes could result in multiple records being returned, inadvertently causing the wrong customer to be contacted or modified. So what we need is a unique attribute which is guaranteed to identify a specific customer. For instance, a unique code might be assigned to each customer, such as CUST-4898. Or frankly, you might simply assign an integer value to each customer, with each new customer being assigned the next integer value in the sequence. So the first customer entered into the system would be assigned the unique value of 1, the next would be assigned 2, and so on and so forth. Well, I would imagine that this approach sounds perhaps a bit too simplistic. It is in actuality incredibly common precisely because of the simplicity. Additionally, you can be guaranteed that no unexpected change in your business or IT environment will affect the use of an integer-based primary key because its only purpose is to serve as the primary key. Otherwise does not play a defining role in the content of its respective row. In any case, this unique value is known as a primary key. Primary keys serve this crucial role in relational database design, not only due to their ability to uniquely identify a record within a single table, but also because they are used within other tables in the context of a foreign key, which links two records together. So next I'd like to offer a few concrete examples demonstrating the use or creation of primary keys. And in doing so, I thought it would be useful to kind of switch gears here a bit and take a look at another very useful and beneficial database for learning purposes, and that is the Sakila database. The Sakila database is bundled with your standard MySQL distribution, so it's already installed and available on your laptop or computer. And you can access that database just like any other. Go ahead and log into your MySQL client, as we've done already several times. And after successfully logging in, go ahead and execute the command use Sakila, and then execute show tables to view a list of tables found in that database. As you can see, there are currently 23 tables. As it might be obvious by simply taking a look at the table names, this database is intended to model a movie store rental chain. We have stores, we have staff members, some information about sales according to store, payment information, tables regarding films, actors within the various films, and so on and so forth. So it's intended to offer a pretty realistic modeling of what a database used within a typical small movie rental chain might look like. And because it's intended for learning purposes, it's properly structured, it's properly normalized, and all around serves as a great example for our purposes. This database was actually created by a member of the MySQL documentation team, a gentleman named Mike Hillier, a few years back. And it was based on an earlier implementation that was put together, believe it or not, by Dell Computing. So it's received quite a bit of attention over the years, and they've certainly tweaked it and in fact continue to maintain it and improve upon it to this day. So the best way, I thought, to take a look at a primary key implementation would be to examine the film table. The film table is actually quite an involved table, so what I will do is actually use a different table structure display syntax rather than use the semicolon, which we've used numerous times so far. I'm going to use the /G it tells the MySQL client to display the table structure in a somewhat different fashion, in a tabular fashion, in fact. So I'll go ahead and press enter, and you can see that each field is being displayed in its own row, if you will. And again, this is merely for display purposes. It just offers a different way to look at, in our case, a rather complex table that, maybe to show the alternate example, that would just kind of spill over and kind of look like quite the mess. So I'll go back and again display this table structure using the /G and scroll up to the top where you will see that the first column is named film_ID, and this is in fact this table's primary key. It's an integer, it's a small int, so it has a rather large range. It's unsigned because we want to be constantly incrementing our integer values with each row insertion and don't really care about the negative side. It's not null because we always want a row to be assigned an integer value, a unique one. It's identified as the primary key. Although the default is null, it never can be null because of the auto increment attribute, which again looks at the previously inserted row, adds 1, and inserts that added integer value to the next row. In the case of the SQL database, they are identifying the primary keys using the name of the table, followed by an underscore, followed by ID. This is just their particular convention for going about naming the primary key. You'll also very commonly see simply ID used. So simply ID as the name of the field, which actually I tend to use. It saves a couple keystrokes and tends to work quite well. I'll go ahead and scroll down just to give you kind of an idea of the content that's stored in this table. I know I'm jumping ahead of myself because we really haven't talked about select statements yet. However, I think you'll find this quite easy to understand. If we go ahead and use a select statement to take a look at a few rows found in this table, it'll become pretty obvious how the auto incrementing primary key works with MySQL. I'll select the film ID, which is the primary key, title, and the release year of the film from the film table. And we're going to order our results by film ID. The default is to order integer values in ascending order, although, as we'll talk about later, you have the option of ordering them in descending order if you'd like. And finally, there are actually a bunch of films in the SQL database. We only need a few to give you a good idea of what, in fact, the table contents look like. We'll just limit our results to 5. I'll go ahead and press enter, and as you can see, the first inserted film was this film titled Academy Dinosaur, which frankly I've never heard of and not even sure it exists. Because it was the first one assigned or added to the table, it has the integer ID of 1 and its release year is 2006. Next one, Ace Goldfinger, film ID of 2, and so on and so forth. So when the occasion arises that we need to absolutely make sure we are referring to African egg, for example, we can attempt to refer to the row by its release year, which obviously isn't going to work, or by its title, which it's certainly possible that 2 or 3 or more movies could in fact share a title. Rather than use either of those columns, we're going to use the primary key. So if we say select title from film where film ID equals 5, we are guaranteed, without a doubt, to receive the row or certain columns within the row associated with that record. And as you'll see in a moment, the primary key also serves a very important secondary role in terms of its relationship when relating rows found in one table within another table. This relationship forms what's known as a foreign key relationship, and we'll talk about that here in just a moment. So you just saw what a primary key looks like within a table after it's already been created, and what the contents of a table consisting of a primary key looks like. But we haven't yet talked about exactly how you would go about creating a primary key. So what I've done is returned to our sample CRM database. And as you can see, notably, I've pulled up the customers table that we had created a few sections ago. What is noticeably missing from this table, after having been introduced to the concept of a primary key, is in fact the primary key, so the automatically incrementing integer value. So what I want to do is go ahead and drop the customers table, which effectively wipes it from our database. and recreate it, this time adding the primary key. As I mentioned in the previous section, I prefer to use the ID keyword for identifying primary keys. So ID, integer unsigned, not null. This should all be familiar to you by now. Adding the auto increment attribute, and finally primary key. And as we've done previously, we'll go ahead and add the other columns. Email, varchar 255, not null. For the purposes of this exercise, I'll just limit it to these three columns. Describe customers, we'll pull up the schema. And as you can see, our primary key field name is ID. It's an integer, it's unsigned, it's not null. It's an auto-incrementing column, and finally it's been assigned the primary key value. Again, without jumping ahead of things too much, we'll demonstrate the fact that the ID column will indeed increment itself by adding a row. Notice how we don't even have to specify the ID column within the list of columns that we want to insert into. I'll just say Jason and add my email address. Go ahead and press enter, and you'll see that we're told that one row has been affected or inserted. And if I select all from customers, you'll see that this is the first row. So it's been assigned the value of 1 for its primary key. So I'll just back on up. Oops, I see I misspelled my email address. We'll just add a second called Sam. Change the email address to make this look a little more realistic. Press enter. Again, we'll take a look at the customer table, and you'll see it's been assigned the value of 2. So adding these primary keys, as was just demonstrated, is quite easy to do, in fact. We just talked about primary keys and the important role they play in uniquely identifying specific rows within our various tables. Next, I'd like to talk about foreign keys, which you can think of as the counterpart to the primary key. When interrelating rows which reside in separate tables within our database, we need a foolproof means of associating this relation. So we have a row identified by a primary key in the actor table, and we have primary keys found in the film table, each of which identify a specific film. What we want to do is create a list of films that a particular actor has starred in. In doing so, we are going to associate their primary keys together in a separate table. So for instance, we know that our actors are in the actor table, our films are in the film table. You'll often see, in regards to associating actors and films together, the approach involves creating another table, typically referred to as a join table. In the case of the SQL database, that table is called actor_film. To illustrate the relationship that this film_actor table is intended to create, I've gone ahead and returned to the SQL database. And as you can see, as a quick recap, we have the actor table, the film table, and the film_actor table. So what I'll do first is go ahead and take a quick look at the actor table. And again, as you can see, the actor_ID column serves as our primary key. And if we select just a few values from that actor table, we can get a feel for what the content looks like. Just limited it to the first 5 values. And again, primary key, it's auto-incrementing. Our first actress in this case is Penelope Guinness. Next, let's take a look at the film actor table. Again, I'll use the /G switch to make this a little bit more legible. You'll see that this table actually doesn't consist of a primary key. And again, it's because this is the join table. We're using what are called foreign keys, which are primary key numbers, in our case, found in other tables, to join 2 specific rows together. We have actor ID and we have film ID. Film ID, of course, referring to the film table. In fact, it's called a composite primary key out of multiple foreign keys. In fact, you can see here, primary key, we're associating an actor ID with a film ID. that row in the film underscore actor table can be uniquely identified by those two integer values. There's only one instance of one actor which can play a starring role or a secondary role in a particular film. Therefore, that combination of integer values is guaranteed to be unique each and every time. So if we go ahead and select just a few rows of our data from the film actor table, you can get a feel for what this looks like. And again, we have actor number 1, which, if I recall correctly, is Penelope Guinness, is associated with the film identified by the primary key of 1. Again, she starred in a film identified by the primary key of 23, and so on and so forth. These two items taken together guarantee that each and every time we're going to have a unique row within this particular table. There's something actually much more important that I want to show you in regards to this table, and that is the concept of foreign key constraints. If Penelope were to suddenly be removed from our database, that is to say, specifically removed from the actor table, we have a serious problem unless certain safeguards are put into place. And that problem is that several rows found in the film underscore actor table will become orphaned. If the Penelope row is destroyed or deleted from the actor table, well then the primary key of 1 no longer exists. Logically, over time, our actor database might be changed or deleted and added to and so on and so forth. We want to make sure, as database administrators or developers, that those changes do not affect the overall quality of the data found in the database. And therefore, by removing that row, we begin to introduce serious data consistency problems into other parts of our database. So what many databases do, MySQL included, is offer this feature known as the primary key constraint. If you look closely back at the table creation structure, you'll see, in fact, that there are two such constraints added to the table. Foreign key, film, actor. This is our reference to the actor. This isn't such an important part of this constraint statement. What I really do want you to pay attention to is this. Our foreign key is the actor ID, which is here, and it references the actor table, and within the actor table, the actor underscore ID primary key. Same concept applies to the film ID. Our foreign key is film ID, references the film table. Now in both cases, you'll see this constraint, and then on update cascade, and again on update cascade. This means that if the primary key found in the reference table, actor and film, were to change, which we know when using automatically incrementing primary keys, we know is really not supposed to ever happen. But nonetheless, if it were to change in one of these tables, MySQL will do the manual change for you within, in our case, the film underscore actor table. So if Penelope Guinness were, for whatever reason, and this is, I stress, highly unlikely when you're using automatically incrementing integers, if her primary key were to suddenly change to 504 within the actor table, then all of the ones found in the actor underscore ID column of film underscore actor will automatically be updated to 504 for you, thus preventing this concept of orphaned records. Furthermore, if because of this constraint, the Penelope row were to suddenly be deleted from the actor table, MySQL is going to prevent that deletion from occurring. It's going to complain. And I can demonstrate this within the MySQL client by attempting to delete her from the database. And I'm going to start what's called a transaction because I don't want to truly affect the Sequila database. This is just for purposes of illustration. I'm jumping ahead of things here by starting what's called a transaction, which we can subsequently roll back any changes which I'm about to make. So don't pay too much attention to the transaction command. What's particularly important is what follows. So I'm going to go ahead and attempt to delete Penelope from the database. So delete from actor, where actor underscore ID equals 1. And we are greeted with an error message. Cannot delete or update a parent row. A foreign key constraint fails. That's good. That means we cannot orphan any records found in film underscore actor. However, if I can first delete Penelope's acting credentials, in doing so, we're not going to affect the quality of the database. We're merely deleting her work. So I'll go ahead and delete those rows. And as you can see, 19 rows have been affected or deleted in this case. We had at least been tracking 19 films that she had played a part in. From here, I can go ahead and delete Penelope from the actor table because there are no more constraints. And sure enough, one row affected. So I really don't want those changes to take place. And because I started that transaction earlier, I can run the rollback command and none of those changes will in fact take effect. Maybe to prove that, again, we're jumping ahead of things here a bit, but I can run select all from film actor limit 5 and you'll see that sure enough, neither the film actor rows nor the Penelope row had in fact been deleted. Now that you've had the opportunity to witness firsthand the benefits of incorporating foreign keys into your relational databases, let's go ahead and try and create one. So what I've done is I've logged in to the MySQL client and switched over to our CRM database. As you can see, the 3 tables that we had created previously, of course, are still there. In addition to a new table called states, this states table is intended to contain a list of all of the states found in the United States. Right now, it's a very simple table consisting of just a primary key, auto-incrementing integer, and the state name. I've also gone ahead and added 2 rows to the table, the state Alabama and Alaska. So next, what we want to do is we want to modify our customers table so that it's possible to associate customer state of residence with the customer. We're going to create a foreign key within that customers table that points to the newly created states table. So what I will do first, just as a quick refresher, I'll show you the customers table. Again, it consists of an ID, name, and email address. And I'm going to go ahead and drop that table and recreate the structure anew. So we will execute the create table statement, adding the primary key, the name, email address. Now this is where the table begins to change. We're going to add a column called state ID, which is a tiny int, it's unsigned, and it's not null. Now notice, if I just scroll up here a bit, how that matches the column definition for the primary key found in the states table. So state ID, tiny int, unsigned, and not null. Next, what we want to do is we want to define that state ID column as a foreign key. So we'll use the foreign key keyword, identifying the column we want to make a foreign key, which is state_ID. It references the states table, and namely the states table's ID column, and our constraint is going to be on update cascade. So with that table creation statement complete, I'll go ahead and press enter, and we'll take a quick look at the schema, and you can see that all of the necessary pieces are in place. Now with the customers table created, let's go ahead and try and add a new record or a new customer to that table. Name, email, state ID. Now remember, we don't need to reference the ID column because MySQL will go ahead and take care of the process of manually identifying and incrementing our primary key each time a new record is created. And our values are JSON, email address, and let's say I live in Alaska. Alaska is identified by the primary key of 2. Select everything from customers, shows that in fact everything has been assigned as we expected. Now because of this constraint, it's important to realize that if we try and add a foreign key to the customers table which doesn't exist, such as 3, we're going to receive an error because that foreign key does not exist, right? We want to make sure that that constraint goes both ways. Furthermore, if we attempted, now that there is in fact a customer associated with Alaska, any attempts to delete Alaska from the states table is going to fail. Again, because of this foreign key constraint. Now, also, I wanted to point out that onUpdate Cascade is only one of several constraints at your disposal. There is also an onUpdate Delete, for instance, and what that will do is it will cascade the deletion across multiple tables, therefore ensuring that no orphan records exist by cleaning out all tables that contain that foreign key and have that constraint on update delete associated with them. Definitely check out the MySQL documentation. In addition to those two, there are a couple other constraints that are worth taking a look at, on delete cascade and on update cascade being probably the most commonplace of those constraints.